When a massive star dies, it doesn't just vanish, it explodes with unimaginable power. From that chaos, something even stranger is born a Magnetar. Tonight we'll uncover how the death of a star can create the most magnetic object in the universe. If you enjoy cosmic mysteries, please like, subscribe and share, and tell us in the comments, what would you ask a dying star if it could answer? Thank you for watching. Now, let's begin. Within a spiral arm of the Milky Way, a massive star burns in quiet isolation. It lies far from the galactic centre where the density of stars and radiation is lower, but still within a region thick with diffuse gas and fine dust. Around it, cold molecular clouds trace long filaments of carbon and hydrogen compounds shaped by magnetic fields that thread through the interstellar medium. These clouds are the birthplace of stars, their gravity slowly condensing regions of gas until nuclear fusion ignites. The star at the centre of this story once formed from such a cloud collapsing under its own weight, until its core grew hot enough for hydrogen atoms to merge into helium, releasing light and heat that have poured outward for millions of years. Its light travels across hundreds of light years, scattering faintly through veils of dust, and its radiation sculpts the edges of the cloud that gave it life. The galaxy's magnetic field runs like invisible lines through this environment, weak compared to the strength of stellar fields, but sufficient to guide cosmic rays and influence the shape of gas. The interstellar medium surrounding the star is not empty. It is filled with atoms and charged particles moving slowly in a tenuous balance of pressure and gravity. Here the life of a massive star unfolds against a backdrop that is both stable and ever-changing. The star itself is immense, with a mass perhaps 10 to 30 times that of the Sun. Its colour leans toward blue-white, a mark of its surface temperature that exceeds 20,000 degrees Celsius. Fusion in its core burns with intense efficiency, consuming hydrogen much faster than smaller stars can. Because it burns so fast, its lifespan is short, only a few million years, a brief flicker on cosmic timescales. Around it may orbit smaller companions or drifting fragments of gas left from its formation, illuminated by its light and pushed outward by its radiation. This radiation pressure drives small particles of dust away, creating a thin, clear bubble in the surrounding gas. In the far distance, other stars glitter faintly, their light dimmed by the same dust that reflects the star's glow. Within the spiral arm, gravity gathers stars into clusters and associations, and this one is no exception. The star belongs to a group of massive suns that form together from the same region of compressed gas. They illuminate their neighbourhood so strongly that the surrounding gas becomes an ionized region, a glowing bubble of plasma stretching across light years. This is an H2 region, named for hydrogen atoms stripped of their electrons by ultraviolet light. Such regions are visible to telescopes as hazy luminous clouds, marking stellar nurseries across the galaxy. Inside this bubble, high-energy radiation interacts with the surrounding gas, heating it to thousands of degrees. The pressure from this heat pushes outward, creating slow waves that ripple through the surrounding dust. Over time, these waves can compress nearby pockets of gas and trigger the birth of new stars. In this environment, the star's presence has a direct and lasting influence. Its strong stellar wind, a continuous outflow of charged particles, streams into space at hundreds of kilometers per second. The wind carves a cavity in the interstellar medium, forming a bow shock where it collides with slower material. Within this boundary, particles are accelerated to high speeds, producing faint X-rays detectable from afar. These processes, though violent by human standards, are steady and predictable. For most of its life, the star maintains an equilibrium between the pressure produced by fusion in its core and the inward pull of gravity. Each layer of its interior contributes to this balance, while fusion steadily transforms light elements into heavier ones. The outer surface of the star appears calm, but beneath it lies turbulence. Convection currents rise and fall, carrying energy outward, while rotation twists the flow of plasma into complex patterns. These motions generate magnetic fields that influence the behavior of stellar wind and surface activity. In the ultraviolet and X-ray bands, the star's emission reveals the scale of its energy output. To nearby systems, its radiation would be lethal, but at interstellar distances it becomes a faint whisper absorbed by clouds of gas. The star's magnetic activity shapes its environment even further, aligning particles and heating regions along field lines that extend for millions of kilometers. The surrounding space also carries the fingerprints of earlier generations of stars. Scattered through the interstellar medium are heavy elements carbon, oxygen, silicon, and iron, released by past supernovae. These enrich the gas from which new stars form, creating a chain of cosmic recycling that links one stellar generation to the next. The current star's own evolution is part of that cycle. It was born from material seeded by explosions that came before, and one day it will add its own remnants back into the galactic mixture. For now, though, it remains steady, shining through layers of dust that scatter its light into soft halos. Observers far away would see it as a bright point, its colour betraying its youth and mass, but nothing yet suggests the immense forces that will one day transform it. The Milky Way itself provides the larger context. From the galactic core to the outskirts, spiral arms sweep through lanes of stars and nebulae, rotating slowly over hundreds of millions of years. The star's position within one of these arms places it amid the most active regions of star formation. Dense clouds energized by radiation and shock waves create a mosaic of glowing filaments. The gravitational tides from the galactic center and nearby stellar associations shape these structures continuously. As the star orbits the center of the galaxy, it moves through varying densities of gas, sometimes encountering turbulent regions that compress its outer wind bubble, sometimes passing through clearer stretches of space. Even on the scale of the galaxy, the star's future is already written in physics. Massive stars cannot last long. Their rapid consumption of fuel ensures an early death. The balance that holds its core stable will one day break when the supply of fusion energy runs out. That moment is still far ahead in the current phase, but the process that will end its life has already begun at an atomic level. Within the core, helium, produced from hydrogen fusion, accumulates and fuses into heavier elements, gradually building layers like those of an onion. Each layer burns at higher temperatures and shorter timescales, moving the star step by step toward instability. For now, the outer layers hide that progression. The light we see comes from the photosphere, the thin region where radiation escapes into space. Below it, pressures and temperatures rise exponentially, and each region is in constant motion. Neutrinos, nearly massless particles born from fusion reactions, stream outward unhindered, carrying away energy that will later play a role when the star collapses. The structure is stable, but only temporarily. The star's enormous luminosity means it loses mass, continuously carried away by its wind, altering the balance of pressure in subtle ways. Over millions of years, that slow loss contributes to the conditions that will eventually lead to collapse. In the quiet interval before its final transformations, the star exists in a delicate equilibrium, an object defined by both its immense power and its finite lifespan. It shines through the dust of its natal cloud, marking one of countless points of light that decorate the galaxy's spiral arms. Around it, silence reigns, disturbed only by the steady hum of radiation and wind. The surrounding gas glows faintly, shaped by its presence but not yet destroyed by it. This is the calm before collapse, a moment of balance in a universe built on motion and change. Deep within the luminous sphere, far below the glowing surface, the structure of the massive star is layered like a nested sequence of furnaces. Each layer represents a stage of its past and a promise of what will come next. At the center lies the core, a region of staggering density and temperature, where fusion reactions have long sustained the delicate balance between the inward pull of gravity and the outward push of energy. The core once fused hydrogen into helium, the simplest and most efficient process for releasing energy, but over time the supply of hydrogen diminished. Now helium fusion dominates, producing carbon and oxygen, while new layers above continue to burn lighter elements in succession. The interior is not static. It is a living system of a nuclear fire where each shell of material burns at its own pace. The deeper one looks, the faster the reactions proceed, and the shorter the lifespan of each stage. In smaller stars, the process stops at carbon or oxygen, but in this giant, gravity ensures it will continue much further. Temperatures in the core reach hundreds of millions of degrees Celsius, forcing atoms together under conditions no laboratory can reproduce. The result is a hierarchy of reactions: carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each of these steps occurs faster than the last as the star struggles to maintain the pressure needed to resist collapse. The entire sequence from the first ignition to the final stage takes only a few million years, a blink compared to the age of the galaxy. The atmosphere of the star hides this interior drama from view. On the surface, the energy generated below rises through convection and radiation, escaping as light. Each photon emitted began its journey thousands of years earlier, in the core, bouncing and scattering countless times before reaching space. Inside, the pressure is immense, sustained by the relentless release of fusion energy. Gravity continually tries to compress the star, while thermal energy pushes outward. The balance between these forces defines the star's lifespan, and every change in fuel or reaction rate subtly alters it. When one layer's fuel is exhausted, contraction resumes, until the next fusion process ignites, temporarily halting collapse. These alternating phases of pressure and release produce the intricate stratified structure that defines late stellar evolution. At the microscopic level, fusion is a battle between opposing forces. Atomic nuclei, all positively charged, naturally repel one another. Only under extreme temperature and pressure can they overcome that repulsion and merge. The deeper the layer, the greater the temperature and the more massive the nuclei being fused. The energy yield decreases with each successive reaction, and eventually a point is reached where fusion no longer provides a net gain. That point will come when iron forms in the core. Iron's nuclei are bound so tightly that further fusion consumes rather than releases energy. When this threshold is reached, the core will lose its main source of outward pressure, setting the stage for catastrophe. For now, though, fusion continues, driving a constant reshaping of the star's interior and a steady outward flow of radiation. Rotation adds another layer of complexity. The star spins, dragging plasma and magnetic fields into sweeping spirals. Differential rotation, where inner layers spin faster than outer ones, twists magnetic field lines and generates internal shear. This motion can redistribute angular momentum and mix material between layers, altering how fusion proceeds. Convection also plays a role. Rising currents of hot plasma carry fresh fuel inward and lift processed material outward. The combined effect of rotation and convection ensures that the star's interior never truly settles. Even as equilibrium holds, turbulence reigns below the surface with zones of intense magnetic activity and shock waves moving through its layers. The chemistry of the star evolves with time. Elements created in fusion are carried outward through mixing and occasionally expelled by strong stellar winds. The outer atmosphere, rich in heavy elements, becomes a source of dust and gas that later contributes to the formation of new stars and planets. Astronomers studying similar stars detect traces of these elements in the surrounding nebulae, evidence of the recycling that shapes the chemical composition of galaxies. The process inside the star is a continuous transformation of matter into energy and back into structure. Every second, enormous quantities of hydrogen are converted into heavier elements, their mass fraction turned into pure radiation. That radiation sustains the luminosity that makes such stars visible across vast distances, yet it also signals the slow depletion of their most important resource. The difference between this star and smaller ones lies in scale. A star like the Sun will spend billions of years on stable hydrogen fusion, while this giant's hydrogen phase lasts only a few million. Its immense mass produces gravitational pressures so strong that it cannot sustain a slow pace of burning. The larger it is, the faster it dies. As the core contracts and heats, the outer layers expand, swelling the star's radius until it may stretch hundreds of times wider than the Sun. The surface cools slightly as it enlarges, but the total energy output increases dramatically. At this stage, the star might appear as a supergiant, its light bright enough to outshine entire clusters. Yet beneath that brilliant exterior, the core contracts relentlessly. The energy flow from core to surface follows precise physical laws. Photons created by fusion scatter repeatedly within the opaque plasma, losing and gaining energy in countless interactions. Deeper regions are dominated by radiation pressure, while outer zones rely on convection. The gradient between these zones is delicate. If the energy flow becomes unstable, parts of the star can briefly pulsate. Such pulsations, though small compared to the star's size, are hints of the tension building within. The star's magnetic field threads through this environment, influencing how heat and matter circulate. Even minor variations in field strength can change how efficiently energy escapes, altering surface activity and stellar wind patterns. In these final evolutionary stages, time accelerates. Helium fusion lasts a few 100,000 years, carbon burning only centuries, and the final stages, oxygen and silicon burning, may last mere months or even days. Each stage releases vast amounts of energy, but also drains the core's ability to resist gravity. The buildup of iron at the center proceeds silently, invisible to outside observers. As it grows, it begins to dominate the mass of the core, pushing it toward the critical limit, where pressure from electrons can no longer support it. Beyond this point lies collapse, yet nothing on the surface betrays the coming event. To any distant observer, the star continues to shine serene and steady, its radiation constant, its color unchanged. All around it, space remains tranquil. The bubble carved by the star's wind expands, gradually filled with a thin plasma. Its edges mark the boundary between the stellar influence and the interstellar medium. Inside that bubble, radiation pressure prevents much external gas from entering, isolating the star from its surroundings. Within, a faint halo of scattered light and dust drifts outward, carrying the fingerprints of the star's evolution. These outer features contrast sharply with the turmoil inside, where pressure and temperature approach limits that matter can barely endure. As the star nears the end of its fuel, the inner regions continue to contract. Neutrinos, nearly massless and unimpeded by matter, escape freely, carrying away energy that hastens the cooling of certain layers. In a subtle interplay, These invisible particles contribute to the changing balance of forces. Gravity grows stronger as the core's density rises. Eventually, the pressure from nuclear reactions will no longer suffice, and the core will begin to yield. The moment of instability when collapse begins is now close. Inside the opaque walls of plasma, the process that will one day lead to a magnetar is already underway. Nothing outside indicates it yet, but deep within the last equilibrium of the star is preparing to break. At the core of the massive star, the chain of fusion reactions approaches its natural limit. Each shell around the center burns a heavier element than the one above it, forming an ordered structure of nested layers. Hydrogen fuses to helium, helium to carbon, carbon to oxygen, and neon oxygen to silicon, and finally silicon to iron. These reactions proceed with astonishing speed, near the end each phase shorter than the one before. The silicon burning phase, the last productive stage, endures for barely a few days. Inside, conditions have become extreme. Temperatures soar to billions of degrees Celsius, and pressures reach beyond imagination. At such extremes, atomic nuclei exist in a dense plasma of protons, neutrons, and electrons. The star's core, now composed mostly of iron group elements, no longer produces usable energy. Iron fusion cannot release additional energy, and so the furnace begins to fail. Gravity, which has been held in check by the outward push of fusion radiation, reclaims dominance. This moment of equilibrium breaking is quiet. The layers above the core still burn furiously, unaware of the disaster unfolding below. But the iron core, growing steadily through silicon fusion in surrounding shells, nears a critical mass roughly 1.5 times that of the Sun, compressed into a sphere only thousands of kilometers wide. When this limit is reached, known as the Chandrasekhar limit, the pressure from electron degeneracy, the quantum force that keeps atoms from collapsing further, can no longer resist gravity. Electrons are forced into atomic nuclei, combining with protons to form neutrons and emitting neutrinos in staggering quantities. In a fraction of a second, the core's composition changes from ordinary matter to neutron-rich matter, and its density increases dramatically. As electrons vanish into protons, the loss of degeneracy pressure triggers runaway collapse. The outer layers of the core, unable to resist gravity, accelerate inward at nearly 1/4 of the speed of light. Temperatures climb even higher, but fusion cannot counteract the implosion. The core shrinks rapidly from thousands of kilometers to only a few tens. Neutrinos produced in immense numbers stream outward in all directions, carrying away energy equivalent to the brightness of an entire galaxy. Yet they barely interact with matter, escaping into space with minimal resistance. The star's core is now collapsing into a form dominated entirely by neutrons. For a brief instant, the outer layers of the star are left suspended, falling inward toward a shrinking center. The density of the collapsing core reaches a level where atomic nuclei themselves touch, forming a solid-like structure of nuclear matter. When the inner core stiffens against further compression, it rebounds, sending a shock wave outward. But this first shock quickly stalls as it encounters infalling material losing energy to the dense gas and to the flood of escaping neutrinos. For a moment, it seems the entire structure may simply collapse without explosion. Yet deep inside, the storm of neutrinos continues to pour from the newborn neutron core, heating the surrounding matter and re-energizing the shock. Meanwhile, above the core, the rest of the star begins to feel the effects of collapse. The layers that had quietly burned silicon and oxygen now descend toward the center, crushed by the loss of internal support. Their fall releases gravitational energy, adding further heat to the chaos. The outer envelope, still opaque to radiation, remains unaware of what is occurring deep within, though the balance is already broken. What once was a stable supergiant star is now a gravitational engine tearing itself apart. In less than a second, the entire iron core collapses from a sphere thousands of kilometers across to one barely 20 kilometers wide. The density reaches that of an atomic nucleus, about 1 billion tons per cubic centimeter. Matter has entered a state where quantum physics dominates completely. The result is a proto-neutron star, a hot, dense remnant formed at the center, spinning rapidly from the conservation of angular momentum. Its rotation, magnetic field, and thermal energy are all rising simultaneously, setting the stage for the birth of something far stranger. The neutrinos continue to escape, but now their sheer number begins to affect the matter above. Each second, about 10 to the power of 50 neutrinos leave the collapsing region. Though most pass through freely, a small fraction interact with the outer layers, depositing energy and reviving the outward moving shock front. This renewed wave begins to push outward, once more breaking through the dense shells of silicon, oxygen and carbon that had surrounded the core. When the shock reaches the outer envelope, the pressure difference becomes enormous. The star's interior erupts. At the surface, the first visible sign of this internal catastrophe will not appear until hours later, when the blast reaches the photosphere. But inside, the transformation is already complete. The core has collapsed, the outward explosion has begun, and a new celestial object, small, dense and rotating, has been born. The transition from star to neutron star is nearly instantaneous. The outer layers, rich with heavy elements, are thrown into space at thousands of kilometers per second. Shock waves race outward, compressing and heating the surrounding medium. The radiation that follows will light up the surrounding gas, turning the site into a glowing nebula. At this stage, the system's energy distribution shifts dramatically. Roughly 1% of the gravitational potential energy released during collapse is converted into kinetic and thermal energy, enough to blow apart the star's envelope. The remaining 99% leaves as neutrinos, invisible to telescopes, but detectable across the cosmos with specialized instruments. The violence of this process ensures that the newborn remnant will begin its existence in a storm of radiation and debris. Inside the forming neutron star, conditions remain extreme. Temperatures exceed 100 billion degrees Celsius. The dense matter behaves as a fluid of neutrons and a few protons, electrons and exotic particles. Magnetic fields, already strong before collapse, are now amplified by compression and rapid rotation. The star spins many times per second, and this rotation winds up magnetic field lines into intense bundles. Within seconds, the magnetic field can reach strengths trillions of times greater than Earth's. At such intensities, it has the power to distort atomic structures and influence the behavior of empty space itself. The core, though stabilized against further collapse by neutron degeneracy pressure, continues to cool rapidly as neutrinos escape. The star's radius settles around 20 kilometers, while its mass stabilizes just above that of the Sun. The shock wave, now sustained by neutrino heating and the release of nuclear energy from recombining particles, accelerates through the outer layers. As it moves outward, it produces an expanding sphere of plasma that will soon emerge as a supernova. In the brief calm that follows the collapse, the remnant at the center begins to define its long-term fate. If rotation is high enough, and the magnetic field reaches the upper limits predicted by theory, the object may become a magnetar, a neutron star whose magnetic intensity dominates its structure and future behavior. For now, that transformation has only begun. The star that once shone steadily for millions of years has ended its life in a fraction of a second, leaving behind a remnant smaller than a city but more massive than the Sun. Around it, the outer layers continue to fall, collide and rebound, releasing light that will soon travel across the galaxy. The balance of forces that once held the star together is gone, replaced by the aftermath of collapse, a moment between destruction and rebirth. In the final instant before collapse, the dense iron core reaches a critical threshold beyond which it can no longer support its own weight. Gravity, unchecked by any further source of outward pressure, drives matter inward at extraordinary speed. The collapse begins quietly but accelerates in less than a heartbeat. Electrons and protons merge into neutrons through a process known as electron capture, producing an immense burst of neutrinos. These ghostly particles flood outward in incomprehensible numbers, escaping the core almost unhindered. As they stream away, they carry with them nearly all of the core's thermal energy. The density of the core climbs past that of an atomic nucleus compressing matter into a solid mass of neutrons packed so tightly that a teaspoon of it would outweigh mountains. The inner core stiffens abruptly, reaching a point where it cannot compress further. At that instant it rebounds. The infalling layers above it strike this surface and ricochet outward, forming a shock front that races toward the surrounding shells. This is the first step of the explosion, though its success is not guaranteed. The shock initially moves outward with enormous energy, but it encounters fierce resistance. As it plows through the star's outer core, it loses momentum, spending energy on disintegrating atomic nuclei into their individual particles. The shock stalls at a distance of only a few hundred kilometers from the center, trapped between the outward pressure of heated matter and the continuing infall of material. For a moment, the fate of the star balances on a knife's edge. Whether it will explode outward or collapse inward entirely depends on the delicate interaction of neutrinos, gravity, and radiation. Within the inner core, the temperature now exceeds 100 billion degrees Celsius. Neutrons, protons, and electrons form a dense fluid of subatomic particles, behaving according to the laws of quantum mechanics rather than classical matter. The newly formed neutron star, still wrapped in layers of falling gas, rotates rapidly, completing several revolutions each second. This rapid rotation winds the magnetic field lines tighter, magnifying their strength. Each rotation drags plasma and field together, amplifying electromagnetic energy that will soon dominate the newborn star's behavior. Meanwhile, the storm of neutrinos escaping from the core begins to play a decisive role. Though these particles rarely interact with matter, their sheer number becomes significant. As they pass through the stalled shock, a small fraction of them collide with infalling particles depositing energy. Over milliseconds, this process heats the region just behind the shockwave, reinvigorating it. The heated matter expands and the shock begins to move again. A second surge of neutrino energy follows, pushing outward with renewed force. Now the wave accelerates, gaining enough energy to break free of the star's gravitational pull. When the shock finally revives, the result is catastrophic. The layers of silicon, oxygen, and carbon above the core are ripped apart and expelled into space. The supernova begins releasing more energy in seconds than the sun will emit in its entire lifetime. The explosion's visible light will later brighten to rival an entire galaxy. But within the first second of collapse, almost all of the energy remains hidden, locked in neutrinos and shock-heated gas. The inner core, now the emerging neutron star, remains buried beneath layers of expanding plasma. At the heart of this chaos, conditions are beyond any known on Earth. The density is so great that space-time itself curves sharply around the remnant. Gravity near the surface is 100 billion times stronger than on Earth. The core's rapid spin flattens it slightly at the poles, producing a shape that is not perfectly spherical. Magnetic fields twist through the dense plasma, threading the star like invisible cables under immense tension. These fields, compressed and stretched by the collapse, grow to strengths measured in trillions of times that of Earth's magnetic field. Within moments, the foundation for a magnetar is laid, though it will take time for its full intensity to emerge. Outside the core, the violence continues. The outward shock encounters successively lighter layers of the star, accelerating as it rises. Each layer adds a burst of light as it is heated to millions of degrees. Behind it, a cavity forms where the pressure of expanding gas pushes outward against the remaining shell. The neutrino flux continues for several seconds, further heating the material and aiding the ejection of the outer envelope. Matter near the equator moves differently than that near the poles, shaped by rotation and magnetic tension. The explosion may not be perfectly symmetric. Instead, it bursts outward in jets and plumes, sculpting the future remnant into a complex pattern. Within seconds, the collapse phase ends. The core has become a stable neutron star, the outer layers are in motion, and the shock has broken through the silicon shell. The star's former equilibrium is gone forever. What remains is a hot, dense, rapidly spinning object surrounded by an expanding cloud of debris. The transition from order to chaos is complete, yet from this chaos, new order will emerge. As the expanding shock tears through the remaining layers, nuclear reactions ignite once again, forming heavy elements that will later drift into space. Gold, platinum, and other rare materials are born in these final seconds, forged by neutron capture in the high-energy environment of the explosion. As the energy moves outward, the outermost layers of the star begin to glow. Photons trapped until now start their journey outward through the opaque plasma. When they finally escape, the light from this explosion will sweep across the galaxy. For a brief time, it will shine brighter than billions of ordinary stars. Yet that moment lies ahead. Deep inside, where the collapse began, the neutron core continues to cool and contract, slightly adjusting to its new state. Its temperature drops as neutrinos carry away the last reserves of heat, leaving behind a dense dark sphere that spins and hums with magnetic power. The entire process from the onset of collapse to the birth of the neutron star has taken less than 10 seconds. In those few moments, the balance between gravity and pressure that governed the star for millions of years has been overturned. The result is one of nature's most violent transformations, a massive star crushed to the size of a city, its outer layers hurled into space, and its heart transformed into one of the densest forms of matter in the universe. The stage is set for what comes next, the awakening of a magnetic force that will dominate the remnant's future and define it as a magnetar. The collapse ends with violence beyond comprehension. As the inner core rebounds against the sudden stiffness of neutron matter, the shock wave born from that impact surges outward through the surrounding layers. It moves faster than the local speed of sound, compressing and heating everything in its path. The density gradient between the core and the overlying shells is steep, and the wave's passage transforms structure into chaos. For a fraction of a second, the shock falters, nearly extinguished by the energy it spends disintegrating atomic nuclei. Yet the ocean of neutrinos pouring from the newborn neutron star breathes new life into it. The revived shock resumes its outward journey, carrying the fury of gravitational collapse into the outer regions of the star. The explosion begins to take shape, a physical manifestation of energy release on a scale no other process in the universe can match, except those involving black holes themselves. The wave moves upward through the silicon shell, leaving behind a region of nuclear fusion triggered by the intense heat. Elements heavier than iron begin to form in this transient furnace, as free neutrons combine with existing nuclei. These heavy nuclei, some unstable, will later decay into stable elements, enriching space with the raw materials for future worlds. The environment behind the shock glows with radiation. Photons trapped for years inside the dense star suddenly find new paths outward as matter thins and expands. A dense plasma of electrons and ions fills the space behind the shock, its temperature measured in billions of degrees. The expanding shock marks the moment when the star's death becomes visible to the universe. As it tears through each successive layer, oxygen, carbon, helium, and hydrogen, it accelerates outward, heating the gas to extreme temperatures. The matter expands and cools in a complex interplay of forces. The outer layers, once stable, are now vaporized and hurled into space at thousands of kilometers per second. The surface, still invisible from outside, begins to ripple under the approaching pressure. When the shock finally breaks free, the star's light will rise suddenly, brightening by millions of times. This moment, known as shock breakout, is the instant when a massive star announces its own destruction. Inside the newborn neutron star rotates rapidly, its spin amplified by the contraction of the collapsing core. Magnetic fields twisted during collapse have grown immensely strong, winding through the plasma like taut threads. The star's surface, if it can be called that, is a layer of super-dense nuclear matter, smooth, opaque, and unimaginably hot. It radiates energy in neutrinos and high-energy photons, forming a pressure gradient that continues to drive the outward flow of gas. The magnetic field channels some of this material along its poles, creating narrow jets of plasma that punch through the surrounding layers at near-relativistic speeds. These jets, though fleeting, shape the symmetry of the explosion, ensuring that it is not a perfect sphere but a more complex structure with lobes and cavities. As the shock advances, it leaves behind a cavity of turbulent material surrounding the neutron star. This region is a furnace of radiation and particle collisions known as the proto-neutron star wind. Charged particles stream away from the surface, interacting with the magnetic field and generating electromagnetic waves that ripple through the expanding gas. The boundary between this outflow and the shock-heated debris is a site of continual interaction, where magnetic energy, kinetic motion, and radiation pressure exchange strength in unpredictable ways. This chaotic region will persist for days as the explosion evolves. The outward moving shock carries with it both destruction and creation. The violence of the explosion tears apart the star's outer structure, but it also synthesizes new elements through rapid neutron capture. Isotopes of gold, platinum, and uranium emerge in the intense neutron-rich environment, destined to drift through interstellar space for billions of years. Long after the explosion fades, these atoms will become part of planets' moons and perhaps living organisms. The same force that ends a star's life seeds the galaxy with the ingredients of future systems. Beyond the immediate destruction, the surrounding space begins to respond. The shock collides with the material shed by the star during its earlier life, shells of gas ejected through stellar winds. Each collision compresses the gas, creating new shock fronts that ripple outward. These interactions produce bright emission across the electromagnetic spectrum X-rays. From the hottest regions, visible light from the cooling gas, and radio waves from electrons spiraling along magnetic fields. Observers far away equipped with telescopes will one day detect this light and trace it back to the site of a long-vanished star. The first moments after the birth shock are a contest between outward expansion and gravitational pull. The outer layers move freely now, but the newly formed neutron star remains bound by immense gravity. Its escape velocity is nearly half the speed of light, yet the material immediately above it surges outward at similar speeds. The shock wave has ensured that only the densest central matter remains confined. What was once the entire mass of a massive star is now divided between an ultra-dense core and an expanding envelope of debris. The light curve of the eventual supernova will depend on how efficiently energy from the core continues to flow into this envelope. The physics governing these processes unfolds in milliseconds. In that time, the magnetic field of the neutron star continues to strengthen, a result of both compression and internal motion. Convection within the core stirs charged particles through the magnetic field, amplifying it through a dynamo process. This internal churning may increase the field by several orders of magnitude, turning a typical neutron star into the seed of a magnetar. The exact amplification depends on rotation, turbulence, and temperature factors that combine differently in every collapse. But even now, before the first stable crust has cooled, the foundations of a magnetar's magnetic dominance are taking shape. As the shock exits the star, its momentum carries the ejected layers outward into interstellar space. The region left behind becomes a hot, expanding bubble surrounded by cooler, denser gas. Over time, this bubble will evolve into a supernova remnant, a structure that will persist for tens of thousands of years. The neutron star, hidden at its center, will continue to emit bursts of radiation and particles as it spins. Its magnetism, rotation, and heat will dictate how it interacts with the debris around it. If the magnetic field grows to extraordinary strength, the remnant will no longer behave like an ordinary pulsar, but as something far rarer and more volatile. In the moments following the birth, shock matter and energy reach a fragile balance. The explosion continues to expand, yet the dense remnant remains intact. The transition from implosion to explosion is complete. From one of the most violent compressions in the universe emerges one of its most magnetic creations. The star's death has released the energy needed to scatter its matter across light years, but it has also left behind a remnant so compact and powerful that it will influence its surroundings long after the glow of the supernova fades. The galaxy now contains a new neutron star, small, dense, spinning and magnetized beyond comprehension, waiting to evolve into a magnetar. At the heart of the expanding cloud, the violence that tore the star apart leaves behind a single object of impossible density. The newborn neutron star measures barely 20 kilometers across, yet contains more mass than the Sun. Within it, gravity is so intense that space itself curves sharply inward. Matter exists in a form found nowhere else, a degenerate sea of neutrons packed so tightly that atomic structure no longer survives. The protons and electrons that once formed atoms have merged, leaving behind a compact body of nuclear matter. The surface, if one can call it that, is a thin boundary between this dense interior and a layer of superheated plasma. From that boundary, heat and particles stream outward, powered by the residual energy of collapse. In the first seconds of its life, the neutron star's temperature exceeds 100 billion degrees Celsius, making it among the hottest known environments in the universe. Inside this new object, the laws of physics behave differently. The pressure that now resists further collapse is not thermal, but quantum mechanical. It arises from neutron degeneracy, a consequence of the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. This resistance halts gravity's inward pull, creating an equilibrium that can persist for millions of years. Yet the balance is delicate. Were the mass even slightly greater, gravity would overwhelm it, and the core would collapse again, this time into a black hole. But here the conditions settle at the narrow margin between stability and oblivion. The density increases toward the center, where neutrons form a fluid so compressed that individual particles overlap. Surrounding this inner core lies a mantle of exotic states of matter, superfluid superconducting regions, and possibly hyperons or quark matter, depending on temperature and pressure. The magnetic field frozen into the plasma during collapse threads through all layers of this interior. As the neutron star rotates, these field lines twist and stretch, generating electrical currents that circle through the dense matter. Every rotation amplifies the magnetic energy stored within. The young star spins dozens of times per second each revolution, winding its magnetic field tighter. The interplay of rotation, magnetism, and density will determine whether this object remains a typical neutron star or evolves into something far more extreme. Outside, the environment is still chaotic. The supernova continues to expand, filling space with gas dust and radiation. Shock waves ripple outward, colliding with earlier shells of material expelled by the progenitor star. The inner region glows with high-energy light powered by radioactive isotopes, such as nickel-56 produced in the explosion. These elements decay into cobalt and iron, releasing gamma rays that heat the expanding gas and sustain its brightness for weeks. At the very center, the neutron star continues to cool through the emission of neutrinos which escape freely through its dense matter. In the first minute of its existence, the star radiates more energy in neutrinos than the Sun will emit in its entire lifetime. The cooling process defines the neutron star's early evolution. As it loses heat, its outer layers solidify into a crust a few hundred meters thick. This crust is composed of nuclei and free neutrons arranged in crystalline patterns under immense pressure. Beneath it, the interior behaves as a neutron superfluid, a quantum state where viscosity vanishes and particles move collectively. The combination of solid crust and fluid interior creates conditions for future instability. Differential rotation between these layers will one day produce sudden shifts in spin observed as glitches in pulsars, but for now the structure is settling, radiating away the remnants of collapse energy and adjusting to equilibrium. Rotation remains the dominant influence in these first moments. The collapse of the progenitor's core has concentrated angular momentum into a much smaller radius, increasing spin rate by orders of magnitude. A star that once rotated once every few days now completes a revolution in milliseconds. The centrifugal force slightly counteracts gravity, flattening the star at its poles. This rapid rotation sustains a powerful magnetic dynamo, which continues to amplify the magnetic field. Charged particles are accelerated along open field lines near the poles, producing beams of radiation that sweep through space like cosmic lighthouses. In time, such beams will create the pulsing signals detected by radio telescopes across the galaxy. For now, the surrounding supernova envelope obscures all direct emission. The dense plasma absorbs light and particles re-emitting them as diffuse radiation. Only neutrinos escape unimpeded. Within seconds, the neutrino flux diminishes as the star cools, but the magnetic field and spin remain. These properties will define its future identity. If the magnetic field stabilizes around a typical neutron star strength, it will emerge as a pulsar. If, however, internal motion and turbulence drive the field far beyond ordinary limits, up to values trillions of times stronger than Earth's, it will become a magnetar. That difference depends on the delicate interplay between convection, differential rotation, and the turbulent fluid motion deep within the core. The atmosphere of the neutron star is only a few centimeters thick, composed of electrons and ions trapped by gravity. Below it lies a region where light cannot travel freely, dominated by degenerate particles. The magnetic field here is so strong that it quantizes the motion of charged particles, altering the very nature of atoms. Radiation escapes primarily along the magnetic poles, forming focused beams of X-rays and gamma rays. The star's gravitational field bends these beams, curving their paths so that more than half of the surface is visible from any external vantage point. Time itself flows differently near the surface, slower than it does in open space. A second at the surface lasts slightly longer, when measured from afar, a subtle but permanent mark of the star's gravity on space-time. The newborn neutron star's energy output reshapes its surroundings. The flow of charged particles creates a wind that expands into the cavity left by the explosion. This wind carries magnetic energy outward, driving shocks through the supernova debris. As it interacts with the outer layers, it forms a luminous structure known as a pulsar wind nebula, a glowing region of synchrotron radiation that marks the star's location. Over the next years, this nebula will expand and fade, leaving behind only faint traces of its initial violence. At the core of this vast structure, the neutron star continues its silent rotation. Its moment of formation has passed, but its influence is just beginning. The star's extreme conditions will persist for eons, a constant source of radiation magnetism and gravitational pull. Each of these forces shapes the evolution of the surrounding space. As the remnant cools further, its temperature drops below 1 billion degrees, and the emission shifts from neutrinos to photons. X-rays and gamma rays now carry away the remaining heat, revealing the star's presence to distant observers. From the outside, the transformation is invisible. The supernova's glow hides the dense object within, but deep inside, the balance of forces stabilizes. A new kind of star has been born, not one of light and fusion, but of gravity density and quantum pressure. It is the final state for most massive stars, a point where matter itself resists further compression. The process that formed it lasted only seconds, yet its consequences will endure for millions of years. This compact object, spinning in silence amid the expanding debris, will soon begin to define itself not only by density but by magnetism. The transition from ordinary neutron star to magnetar is about to begin. Inside, the young neutron star motion has not yet ceased. Its interior churns with turbulence left over from the violent collapse. The rapid rotation that now defines its structure drives differential motion between layers, and the extreme heat keeps the matter fluid rather than solid. Convection rises and falls in enormous currents, each carrying charged particles through the dense medium. This motion, occurring within a sphere already threaded by magnetic fields, becomes the engine of amplification. What began as a magnetic field inherited from the progenitor star already strong by ordinary standards now grows to unimaginable strength. The process is not mechanical in the familiar sense. It is the action of a dynamo operating in conditions of nuclear density. Each rotation twists magnetic field lines, stretching and folding them until they multiply in intensity. Within seconds, the field strength surpasses anything known elsewhere in the universe. In the hot, dense fluid, neutrons dominate, but a fraction of protons and electrons remain. These charged particles are essential for the dynamo process. As they move within the rotating fluid, they create electrical currents that reinforce the existing field. The faster the star spins, the more efficiently the dynamo works. Rotation rates of several hundred times per second generate enormous magnetic tension, and every fluctuation within the core adds another layer of complexity. The field becomes tangled and unstable, coiling through the star's interior like threads under strain. In places, it breaks and reconnects, releasing energy as bursts of heat and radiation. The magnetic energy density soon rivals the gravitational binding energy of the crust itself, and the newborn neutron star crosses the threshold into a new identity, the seed of a magnetar. This amplification happens in silence. From the outside, no visible sign betrays what is unfolding within. The star's surface remains hidden behind layers of debris, its light absorbed by the surrounding supernova. But inside, magnetic fields interact with rotation to sculpt the internal structure. magnetic pressure reshapes the fluid distribution, creating regions where density and temperature differ from their surroundings. The field may concentrate near the poles, forming bundles of lines that emerge through the surface and connect back at the equator. The result is a geometry far from simple, twisted, asymmetrical, and capable of storing vast energy. The same field that grows inside also escapes outward. Magnetic flux anchored in the crust rises through the star's surface, carrying electric currents into the surrounding plasma. These currents accelerate charged particles to near-light speeds, generating intense electromagnetic radiation. The field lines extend millions of kilometers into space, forming a magnetosphere, a bubble of magnetic influence enclosing the star. Within this region, plasma co-rotates with the star bound by magnetic tension. As rotation continues, the field lines wind outward, forming spirals that carry energy away as a continuous wind. This magnetized wind will later shape the nebula around the star, imprinting the geometry of its birth upon the expanding supernova remnant. In the core, the amplification persists until the available energy is balanced between rotation-convection and magnetic tension. The turbulence that began during collapse gradually subsides as the star cools. The magnetic field, however, remains frozen into the dense matter. It cannot dissipate easily because the interior behaves as a superconducting fluid where electrical resistance vanishes. The field lines become locked in place, preserved for millennia. Even as the star's rotation slows, the magnetic energy will remain trapped, shaping its long-term evolution. The Magnetar's field strength now exceeds 10 to the power of 15 Gauss trillions of times stronger than Earth's. At such levels, the field influences everything it touches. It alters the motion of electrons, confines radiation to narrow channels, and changes the properties of space itself. Quantum effects appear on macroscopic scales. Photons split into pairs. Vacuum, polarization modifies the way light propagates, and atomic structures are stretched into elongated forms, aligned with field lines. Near the surface, the atmosphere is compressed into magnetic columns, where matter behaves differently from any terrestrial state. This immense magnetism transforms how the star interacts with its environment. The magnetic poles become regions of concentrated energy, where particles are accelerated outward in narrow jets. These jets emit high-energy radiation, primarily X-rays and gamma rays, that pierce through the surrounding debris once it thins enough. The rotational energy of the magnetar drives this emission, converting mechanical motion into electromagnetic power. Every rotation sends pulses of energy through the magnetosphere, which radiates into space as coherent beams. Though invisible for now, these emissions will later become the distinctive signature of a magnetar, sporadic, intense, and far brighter than any ordinary pulsar signal. Beneath the crust, the stress created by the field begins to build. Magnetic pressure twists the solid outer layer, storing tension that will one day break the crust apart in sudden, powerful bursts. For now, the crust is still forming, cooling from the immense heat of collapse. As it solidifies, it locks the magnetic field in place, anchoring it to the structure below. The field lines that penetrate the crust act like steel cables, under enormous strain, waiting for the slow rearrangement of forces that will eventually trigger future outbursts. The star's rapid rotation gradually slows as magnetic braking takes effect. The same magnetic field that channels energy outward also carries away angular momentum. The neutron star's spin period lengthens over seconds, then minutes, then hours, as its rotational energy is converted into radiation. The loss of spin is rapid compared to that of an ordinary pulsar because the magnetic field acts as an efficient brake. Within a few thousand years, the star's rotation rate will drop from hundreds of revolutions per second to less than 1. Yet even as it slows, the magnetism remains unweakened, continuing to dominate every process in and around the star. Outside, the expanding supernova remnant begins to reflect the central engine's influence. Magnetic energy injected into the ejector creates asymmetries, forming bright filaments and knots of gas. X-ray observations of such remnants in the future will reveal these imprints, curved arcs, polarized emissions, and regions of shock heating caused by magnetic reconnection. The magnetar's presence, though hidden within the dense core, is written across the surrounding space. In the brief time span since the collapse, the star has changed from a nuclear furnace into a quantum object of pure density and magnetism. The same forces that ended the old star's life now sustain a new kind of stability. The field coiled deep within acts as a memory of the collapse energy captured and frozen in form. Though the violence of its birth is fading, the power it holds is only beginning to manifest. The magnetic amplification that occurred within seconds of its creation has determined its destiny. From this moment onward, the neutron star is no longer ordinary. It is now a magnetar, a stellar remnant defined by magnetism so extreme that it will reshape everything it touches. As the newborn neutron star settles, its magnetic field reaches extraordinary intensity. The amplification that began deep within has now frozen into the structure, locking vast energy into the solidifying crust. The field's configuration is far from simple. It loops outward from the poles, curves through the star's magnetosphere, and returns to the equator in a complex weave of charged currents. In some regions, the field is ordered, forming smooth arcs. In others, it is twisted and unstable. This combination of symmetry and distortion defines the magnetar's nature. While most neutron stars retain fields of 1 trillion Gauss here, the strength exceeds 10 quadrillion. At such magnitude, magnetism is not merely a force, but a framework shaping matter, radiation, and even space itself. The surface now glows with residual heat and magnetic tension. As the outer layers cool, they contract, slightly straining against the field that threads through them. The solid crust, still only a few hundred meters thick, begins to bear stress at levels beyond anything known in ordinary physics. Microscopic shifts within the crystalline lattice release bursts of energy that flash across the spectrum from radio to gamma rays. These early disturbances mark the first evidence of a magnetar's restless behavior. Outside, the magnetic field dominates the surrounding space. It extends far beyond the star's radius, forming an enormous magnetosphere. Within this region, plasma particles are bound to magnetic lines that rotate with the star locked in its field like iron filings frozen in motion. The rotation drags the field through space, creating immense electric potentials. Electrons are ripped from the surface and accelerated to near the speed of light, spiraling along curved paths that emit synchrotron radiation. The result is a continuous glow of high-energy light emanating from the poles. As the star spins, this emission sweeps through space like a cosmic beacon. Yet the intensity is irregular. Magnetic tension rearranges itself unpredictably, leading to intermittent pulses and flares. The environment near the star is unlike any other in the universe. The magnetic pressure exceeds gravitational pull at the surface, and quantum effects become visible on macroscopic scales. Atoms cannot exist in their familiar form. Instead, electrons are forced into elongated states aligned with the magnetic field, creating structures stretched like thin threads. Photons move differently here, their paths bent, not only by gravity but by the polarization of the vacuum itself. Space, normally empty, behaves as a medium distorted by magnetic energy. In this region, even light cannot travel freely in all directions. The magnetar's field filters radiation, splitting it into components that move at slightly different speeds. Over time, this effect creates the polarized emissions that astronomers will later observe as signatures of magnetars scattered throughout the galaxy. The surface of the magnetar remains incandescent, though it cools rapidly compared to the first moments after collapse. Its temperature falls from tens of billions of degrees to mere millions, yet the radiation it emits still lies in the X-ray range. The crust solidifies completely during this cooling phase, encasing the inner core in a rigid shell. Within that shell, the intense magnetic stress continues to build. Magnetic loops emerging through the surface twist and reconnect, releasing sudden flares of energy. Each reconnection event can unleash as much power as the sun radiates in a century. These flares travel outward along the field lines, disturbing the plasma of the magnetosphere. The surrounding space becomes a storm of charged particles, light, and electromagnetic waves. For a few moments, the energy output rivals that of an entire galaxy, before fading again to quiescence. At the same time, the magnetar's rotation continues to slow. Every pulse of radiation carries away angular momentum. The strong magnetic field acts as a brake, converting rotational energy into radiation that escapes into space. The process is steady but efficient. In just a few thousand years, the star's spin period will lengthen from milliseconds to several seconds. This deceleration changes the structure of the magnetosphere. As the rotation slows the light cylinder, the distance at which co-rotating magnetic field lines reach the speed of light moves closer to the surface. The field beyond that point opens into space, allowing particles to escape in winds that interact with the surrounding supernova remnant. These winds inflate a nebula of magnetized plasma that expands outward at thousands of kilometers per second, glowing faintly in X-rays. Within the magnetar's crust, stresses accumulate faster than they can be released smoothly. When the pressure exceeds the crust's breaking strength, the lattice fractures. These events, called starquakes, send seismic waves through the solid outer layers, briefly altering the star's shape and rotation rate. The sudden shifts in geometry can release bursts of radiation across the electromagnetic spectrum. Some of these flares last only milliseconds, others endure for minutes. Each one injects new energy into the magnetosphere, where it is converted into light and particle acceleration. Observers far away will one day detect these flares as short, intense flashes of gamma rays, the telltale signatures of magnetar activity. The magnetar's surrounding environment reflects its internal energy. The expanding debris of the supernova still glows faintly, lit from within by radioactive decay, but the magnetic outflows carve new structures into it. Jets of charged particles emerging from the poles drill narrow channels through the gas. These jets eventually break free, releasing knots of magnetized plasma that move outward into the interstellar medium. The collisions between these outflows and the slower-moving supernova debris generate shocks that heat the gas to millions of degrees. As the magnetar ages, the nebula around it becomes a vast filamented cloud of glowing matter, shaped entirely by magnetic pressure and rotational energy. Over years and centuries, the magnetar's surface cools further, its heat replaced by magnetic activity as the main energy source. The balance between cooling and magnetic dissipation determines its future evolution. Inside the superconducting core traps magnetic flux lines that can drift slowly through the dense matter. As they move, they alter the field structure, twisting it even more and occasionally triggering new bursts. This slow rearrangement of internal magnetism ensures that the magnetar remains active long after its rotation has slowed and its surface has cooled. The transformation from neutron star to magnetar is complete. What remains is an object smaller than a city, yet holding more magnetic energy than entire star systems. It no longer shines by fusion or by gravitational collapse, but by the release of magnetic stress. Every motion within it, every rearrangement of its internal field can release immense energy into space. The Magnetar's existence represents one of nature's most efficient mechanisms for converting internal energy into radiation. Its surface, though quiet between flares, is never truly still. Underneath, magnetic tension continues to twist the crust and distort space around it. The Magnetar stands now as a paradox of power and restraint, infinitely dense, incredibly small, and almost perfectly stable, yet capable of eruptions that outshine galaxies. It is the universe's ultimate magnet, the product of collapse and compression of gravity, balanced by quantum pressure and magnetism. The calm that follows its birth is temporary. Within it, stored energy waits ready to break forth when equilibrium fails. In the silence of interstellar space, this object rotates steadily invisible for now within its expanding cocoon of gas and dust. But already its field reaches far beyond the debris threading into the surrounding medium and leaving its imprint on the galaxy. The birth of a Magnetar marks not an end, but the beginning of a new and lasting force in the cosmos. In the first years after its creation, the Magnetar reveals its presence through sudden bursts of light and energy that pierce the darkness around it. The intense magnetic field that defines its existence continues to shift and settle, twisting within the solid crust and releasing stored energy in violent pulses. These events, known as magnetic reconnection and crustal fractures, generate enormous flares that bathe space in X-rays and gamma rays. The process begins deep within the crust, where magnetic stresses build slowly until the crystalline lattice gives way. When the fracture occurs, the rearrangement of field lines releases energy almost instantaneously. The resulting electromagnetic surge races outward along the magnetosphere, accelerating particles and producing a wave of radiation that can outshine the combined light of every star in the Milky Way for a brief instant. Such eruptions mark the Magnetar's earliest and most volatile period, when its internal field remains dynamic and unstable. The radiation emerging from these events travels outward through a magnetosphere shaped by extreme forces. Magnetic field lines form arches and loops around the star, confining charged particles in intricate patterns. When a flare occurs, these loops snap and reconnect, hurling plasma outward at relativistic speeds. The trapped particles spiral along the field lines, emitting synchrotron radiation that spans the electromagnetic spectrum. In high-energy wavelengths, this appears as an intense short-lived flash, followed by a gradual decline. To distant observers, these flares manifest as bursts of gamma rays, brief but powerful signals that fade within seconds. Occasionally, when several reconnections occur in sequence, the emission continues for minutes, producing what astronomers call giant flares. These events release energy equivalent to millions of years of solar output and can be detected across galaxies. Between these eruptions, the Magnetar does not remain dormant. Its surface emits steady X-rays from residual heat and magnetic activity. The emission is modulated by the star's rotation, producing periodic pulses that reveal its spin rate. Each pulse corresponds to one rotation of the Magnetar, allowing astronomers to measure how quickly it slows over time. The gradual loss of rotational energy confirms the immense strength of its magnetic braking. Even in quiet phases, the Magnetar's magnetosphere remains alive with currents and radiation, producing a persistent glow of X-rays that slowly diminishes as the star cools. This persistent emission is thought to result from the continuous rearrangement of the internal magnetic field which transfers energy to the surface through the crust. The region surrounding the Magnetar reflects its violent nature. The expanding supernova remnant still envelops the star, glowing faintly from radioactive decay and shock heating. Within it, the Magnetar's radiation creates cavities and bubbles of ionized gas. Each flare adds new structures to the surrounding plasma, sculpting filaments and arcs that expand outward at thousands of kilometers per second. As the high-energy radiation collides with dust and gas, it triggers further emission across the spectrum, creating a brief but brilliant interplay of light and shadow. Over decades, the nebula around the Magnetar becomes a dynamic environment of shock fronts, turbulence, and radiation echoes. On the surface itself, physical conditions are beyond comprehension. The magnetic field strength distorts the crust, creating tension, equivalent to billions of tons per square meter. When the crust fractures, it sends seismic waves across the surface, briefly altering the star's rotation rate. These small irregularities, called glitches, are the fingerprints of deep internal change. They occur when angular momentum stored in the fluid interior transfers suddenly to the crust, producing a measurable acceleration in spin. Each glitch releases additional energy, sometimes triggering new flares. The interplay of spin magnetism and crustal stress defines the Magnetar's erratic rhythm, a pattern of calm punctuated by violent release. Radiation from the Magnetar interacts strongly with its environment. The intense magnetic field traps charged particles and forces them to co-rotate with the star. As these particles move, they emit beams of radiation that escape along the open field lines near the magnetic poles. The beams are narrow and directional, producing the periodic pulses that characterize magnetars in their quieter phases. The alignment of the magnetic and rotational axes determines whether these pulses are visible to distant observers. When viewed from Earth, a magnetar may appear as a pulsating source, its brightness rising and falling with each rotation. Unlike ordinary pulsars, whose emissions are driven primarily by rotation, the Magnetar's beams draw energy from magnetic decay. The early outbursts play a crucial role in defining the Magnetar's long-term evolution. Each flare rearranges the field lines and relieves internal stress, gradually stabilizing the configuration. The frequency of eruptions decreases as the magnetic field settles into a more stable geometry. In the first decade, flares may occur frequently. After centuries, they become rare. Yet even as the violence subsides, the Magnetar remains extraordinarily energetic compared to other neutron stars. Its quiescent luminosity can exceed 100,000 times that of the Sun, sustained entirely by magnetic energy rather than fusion or rotation. Beyond its immediate surroundings, the Magnetar's radiation influences interstellar space. Gamma rays from giant flares ionize distant clouds of gas, while relativistic particles streaming from the magnetosphere create shock waves that propagate through the supernova remnant. These processes contribute to the complex evolution of the nebula, adding layers of structure and energizing its material long after the explosion itself has faded. In some regions, collisions between high-speed particles and dust grains produce faint optical emission, creating a halo of scattered light. To future observers, this faint glow will mark the position of a once violent event, a remnant slowly dispersing into the interstellar medium. Inside the Magnetar, the internal processes that drive this radiation continue. The magnetic field slowly diffuses through the superconducting core, transferring energy outward. As this energy emerges, it heats the crust and powers the persistent X-ray emission. Occasionally localized instabilities within the magnetic field trigger sudden reconnection events that produce short, powerful flares. These flares release not only light but also particle winds that carry energy far beyond the Magnetar's immediate environment. The cumulative effect of these outbursts is to maintain the Magnetar's influence over its surroundings long after its birth. The energy output of a single flare can alter the star's magnetosphere permanently. Each burst redistributes plasma and reconfigures the field lines, changing how radiation escapes. After a particularly strong eruption, the Magnetar's pulse pattern may shift its brightness, varying unpredictably until the magnetosphere re-establishes equilibrium. This ongoing adjustment ensures that no two Magnetars behave identically. Each carries a unique history recorded in its field geometry, rotation rate, and emission profile. Over thousands of years, these differences will define the diversity observed among Magnetars across the galaxy. The early outbursts mark the Magnetar's first dialogue with the cosmos. They announce the presence of a new kind of star, one that radiates not by burning fuel, but by untangling magnetic knots forged in the moment of its birth. In this brief era, the Magnetar is both creator and destroyer, shaping its environment through waves of energy that echo across space. As time passes, the frequency of flares diminishes, but their memory remains in the nebula's patterns and in the trails of charged particles moving outward into the galaxy. The violence of these first years is the Magnetar's way of becoming stable, its means of turning the raw energy of collapse into equilibrium. From now on, its power will endure in quieter forms, its light persistent, its magnetism eternal. The debris from the explosion continues to move outward, carrying the elements forged in the star's final moments into the vastness of space. What began as a violent collapse has now become a slow expansion, a visible echo of the star's death. The supernova remnant grows each day, its outer edge racing away at thousands of kilometers per second. Shock waves compress the surrounding gas, creating a thin shell of glowing material that radiates invisible light, X-rays and radio waves. Inside this shell, turbulence reigns. Filaments of ionized gas twist and fold, sculpted by the competing pressures of heat motion and magnetic energy. At the center lies the Magnetar, a point-like remnant hidden within a storm of radiation, its magnetic field still shaping the evolving nebula that surrounds it. The expanding material cools as it grows, but it remains hot enough to glow across the electromagnetic spectrum. Elements synthesized in the explosion, oxygen, silicon, sulfur, calcium, and iron, emit distinctive lines of light that astronomers can one day identify. Each element reveals the temperature and density of the gas, allowing future observers to reconstruct the dynamics of the blast. In these early years, however, the remnant is opaque and bright, its radiation trapped and reprocessed by the thick plasma. Gradually, as it expands and the density drops, the interior becomes transparent. The hidden core begins to influence the structure of the surrounding gas, creating a faint central glow powered by the Magnetar's rotation and magnetic energy. Within the remnant, the Magnetar drives a continuous wind of charged particles that collides with the slower-moving ejector. The collision forms a boundary known as a termination shock, where the Magnetar's energy is transferred to the nebula. The region between the Magnetar and this boundary becomes a pulsar wind nebula, an expanding bubble of relativistic particles trapped by magnetic fields. The radiation from this nebula shines in X-rays and gamma rays, illuminating the surrounding material from within. As the shock front propagates outward, the nebula expands asymmetrically, shaped by variations in density and the orientation of the magnetic field. In some directions, the expansion is faster. In others, the dense gas of the progenitor's stellar wind slows its progress, producing complex patterns of brightness and shadow. The magnetic field of the Magnetar extends beyond the immediate nebula, reaching into the ejector. The field lines guide the motion of charged particles, channeling them into streams that trace invisible paths through the plasma. These streams create fine filaments observable in later stages of the remnant's evolution. Their curvature and polarization reveal the presence of magnetism on scales of light years. The energy carried by the Magnetar's wind keeps the nebula inflated long after the explosion's initial power fades. Even when the outward shock begins to slow under the weight of interstellar gas, the internal pressure from the Magnetar's wind maintains the remnant's luminosity. Outside the main shell, the shock wave sweeps up interstellar matter, heating it to millions of degrees. This forward shock marks the expanding edge of the remnant. Behind it, a reverse shock travels inward, compressing and reheating the ejector. The interaction between these two shocks creates a layered structure of gas at different temperatures and velocities. X-ray emissions trace the hottest regions near the forward shock, while optical and radio emissions arise from cooler, denser filaments closer to the interior. The overall appearance is a sphere of glowing gas threaded by delicate lines and knots, a relic of both destruction and creation. Over time, the remnant's expansion slows as it accumulates mass from the surrounding medium. The kinetic energy of the explosion disperses into heat and radiation, and the once smooth shell becomes fragmented. Dense clumps of material enriched with heavy elements begin to detach and drift through space. Each fragment carries the chemical fingerprint of the original star, a mixture of elements that will later seed new generations of stars and planets. The Magnetar at the center continues to inject energy, ensuring that the nebula remains visible for thousands of years. The combination of expansion, radiation, and magnetic interaction transforms the immediate surroundings into one of the most luminous structures in the galaxy. The physical conditions within the remnant are extreme but transient. Temperatures of millions of degrees slowly decline, and the expanding gas cools as it mixes with the interstellar medium. Radiation from the Magnetar, though less violent than its early flares, continues to heat nearby regions, maintaining pockets of high-energy plasma. The distribution of elements becomes increasingly uniform as turbulence mixes the ejector. In this way, the products of the supernova merge with the larger environment, contributing to the galactic cycle of matter. What was once a single massive star becomes part of a diffuse network of gas that will over millions of years form new stars and worlds. The expanding remnant serves as a vast laboratory of physics. Shock fronts accelerate particles to near the speed of light, producing cosmic rays that escape into the galaxy. Magnetic fields amplify under compression, influencing how energy and matter distribute themselves. The nebula's brightness varies with time as the Magnetar's energy output fluctuates. Flares and winds from the central object send waves of radiation through the nebula, briefly illuminating structures before fading again. Each pulse leaves a signature, a ripple of light expanding outward at the speed of radiation fading into the general glow. Beyond the immediate boundaries of the remnant, the interstellar medium begins to feel its influence. The shock wave drives a growing bubble of hot gas into the surrounding space, compressing and heating interstellar clouds. In some cases, these clouds collapse under the new pressure, triggering the formation of new stars. Thus, the death of one star becomes the seed of many others. The Magnetar, still buried within the fading glow of the supernova, continues to contribute energy long after the initial explosion has passed. Its magnetized wind ensures that the process of transformation continues for millennia, shaping the composition and structure of the nearby galaxy. From the outside, the remnant expands in silence, a sphere of faintly glowing filaments drifting through space. To an observer far away, it is a sign of both destruction and renewal. The light from the explosion will have already passed, but the faint afterglow persists, marking the site where a star once lived and died. At its core, the Magnetar remains hidden, small, dense, and incomprehensibly powerful. Its radiation, invisible to the human eye, continues to move outward, shaping the nebula and influencing distant space. Over tens of thousands of years, as the remnant fades and disperses, the Magnetar will emerge alone in the dark, surrounded by the relics of its birth. Yet the material it expelled will not vanish. It will drift cool and gather again under gravity's slow pull, becoming the foundation for future generations of stars. In this way, the cycle of stellar life continues, each death enriching the next birth, and the story of one Magnetar becomes part of the galaxy's larger history. At the heart of the expanding supernova remnant, the Magnetar continues to pour energy into its surroundings. Its rotation and magnetic field act as a central engine, driving a constant flow of charged particles outward. This stream of matter and electromagnetic energy, known as the Magnetar wind, interacts with the slower-moving supernova debris, forming a luminous and turbulent region called a Magnetar wind nebula. Unlike the smooth, symmetric light of the initial explosion, this nebula is intricate and restless. Waves of radiation pulse outward, sculpting structures that twist and ripple through the gas. The expanding shell that once defined the boundary of the supernova now glows from within, lit by the Magnetar's invisible hand. Each rotation of the star pumps new energy into the nebula, maintaining its brightness long after the explosion's initial heat would have faded. The wind itself originates from the magnetosphere, where magnetic field lines anchored to the star's surface accelerate particles to near-light speeds. These particles, mostly electrons and positrons, stream outward along the open field lines at the poles. As they escape, they spiral around the magnetic lines, emitting synchrotron radiation that covers the entire electromagnetic spectrum. The radiation pressure from this process pushes against the surrounding gas, inflating a cavity of hot plasma around the star. The boundary between this magnetized bubble and the denser ejecta of the supernova becomes a region of intense turbulence and shock heating. This is where the Magnetar's rotational energy is converted into observable light. Inside, the nebula motion is constant. Magnetic fields twist and fold, guiding charged particles into filaments and arcs that glow in X-rays. The nebula expands at thousands of kilometers per second, its inner edge driven outward by the steady pressure of the Magnetar wind. The structure is not static. It breathes and shimmers as bursts of energy from the Magnetar's surface propagate outward. Each flare produces a shock wave that races through the plasma, momentarily brightening the entire region. Observed from a distance, such events would appear as irregular fluctuations in the nebula's luminosity, a flickering signal of the star's internal activity. The density and temperature within the nebula vary with distance from the Magnetar. Closest to the star, the plasma is extremely hot and thin, dominated by high-energy particles and magnetic fields. Farther out, where the wind collides with slower-moving supernova ejecta compression, forms denser regions that radiate strongly in visible and infrared light. These layers form concentric shells of emission, each tracing a boundary between regions of differing energy. The result is a complex mosaic of matter and light, where radiation, magnetism, and motion continually reshape one another. The Magnetar's rotation is slowing, but the stored energy in its spin remains immense. With each turn, a fraction of this rotational energy is converted into magnetic and kinetic energy carried by the wind. Over years and centuries, the spin-down power decreases, but even as it fades, the Magnetar continues to sustain its nebula. The rate of energy loss defines the brightness of the surrounding structure. For some magnetars, this power output remains high enough to keep the nebula luminous for tens of thousands of years. During this time, the radiation from the nebula contributes significantly to the heating and ionization of the local interstellar medium. The Magnetar Wind Nebula evolves through distinct stages. In its earliest phase, expansion dominates, and the boundary between the nebula and the outer ejecta moves outward rapidly. As time passes, the expanding supernova shell slows under the weight of accumulated interstellar gas, and the nebula begins to push back against it. The resulting compression generates additional shocks that heat the gas, once more reigniting emission that had begun to fade. In this middle stage, the nebula becomes filamented, its structure divided into networks of bright threads. The interplay between magnetic tension and pressure gradients creates patterns reminiscent of turbulence in a liquid, though on scales of light years. Eventually, as the magnetar loses rotational energy, the power driving the wind diminishes. The nebula's brightness begins to decline, and the expansion slows. The boundary between the inner nebula and the outer supernova shell grows more diffuse, and the magnetic field lines stretch and relax. Yet even in this quieter state, the magnetar's field continues to influence its surroundings. The particles it has accelerated remain trapped within the expanding plasma, radiating faintly in radio wavelengths. The nebula transitions from a brilliant high-energy structure to a relic of soft light still visible as a reminder of the energy once released from the star's death. Within the nebula, magnetic reconnection remains a powerful mechanism for energy release. As the field lines twist and interact, they periodically break and realign, converting stored magnetic energy into kinetic energy of particles. These reconnection events produce localized flashes of radiation that can briefly brighten the nebula. Over time, this ongoing process redistributes the magnetic field, smoothing out irregularities and allowing the system to approach equilibrium. However, the magnetar's field is so strong and complex that complete stability is never achieved. The nebula remains a living structure, its form continually reshaped by forces originating at its core. The scale of the Magnetar Wind Nebula extends far beyond the size of the original star. Within a few thousand years, it can reach several light years across, large enough to encompass multiple solar systems. Its outer edge interacts with the interstellar medium, sweeping up gas and dust and compressing it into a thin shell. In some regions, this compression may trigger the formation of new stars, continuing the cycle of stellar evolution. Thus, the energy released by one star's death becomes the catalyst for the birth of others. The magnetar's influence, though, concentrated in a small region of space, ripples outward across the galaxy. To future observers, long after the initial explosion's light has faded, the nebula will remain a beacon of residual power. Its faint X-ray and radio emissions will mark the site of a long-vanished supernova. At its center, the magnetar will persist as a compact source spinning slowly, now its magnetic field gradually decaying but still strong enough to control the surrounding plasma. The nebula will continue to expand and cool, blending eventually with the interstellar background. When it does, the elements it carries, iron, oxygen, and carbon, will enrich the galactic medium, ensuring that the materials forged in the heart of the long-dead star are not lost. The Magnetar Wind Nebula represents the visible legacy of the star's violent transformation. It is the bridge between destruction and creation, where magnetic energy and expanding matter coexist in a delicate balance. Within its luminous filaments, the record of collapse, explosion, and rebirth is written in light. Though it will one day fade, the nebula's influence endures in the stars that follow, in the dust that condenses into planets, and in the atoms that make up all future forms of matter, From the collapse of one massive star comes a cascade of renewal, a reminder that even in the universe's most violent events, the cycle of energy and creation never ends. As centuries pass, the Magnetar begins to cool. The intense heat left from its violent birth radiates steadily into space first, through neutrino emission, then through X-rays and soft gamma rays. In its early years, cooling occurs rapidly, driven by the enormous temperature gradient between the interior and the vacuum outside. Neutrinos escape easily from the dense matter, carrying away energy at a prodigious rate. After the first few thousand years, when neutrino emission becomes less efficient, the surface temperature falls to a few million degrees Celsius, and the glow of X-rays dominates the remaining radiation. The Magnetar's crust, once molten and shifting, hardens completely, forming a solid layer of immense rigidity. Beneath it, the neutron superfluid continues to rotate freely, largely isolated from the crust by quantum effects. This separation of layers introduces one of the most curious characteristics of neutron stars: the difference between the rotation of their solid and liquid parts, a delicate imbalance that will occasionally reveal itself as a sudden change in spin. Rotation, which was once blisteringly fast, has slowed dramatically by this stage. The same magnetic field that gave the Magnetar its power now acts as a brake, converting rotational energy into radiation and particle winds. Each rotation sends electromagnetic waves through the magnetosphere, carrying away momentum. The rate of deceleration depends on both magnetic strength and angle between the magnetic and rotational axes. For a typical Magnetar, the spin period lengthens from milliseconds at birth to several seconds after 10,000 years. The process of slowing is smooth but not uniform. Occasionally, the crust experiences shifts or fractures that transfer angular momentum between layers, producing small jumps in the star's rotation rate. These events, called glitches, are measurable consequences of the star's internal physics, a sign that the core and crust remain coupled only imperfectly. As rotation decreases, the Magnetar's field configuration also evolves. The twisted field lines that once extended far into space begin to relax. The magnetosphere contracts slightly, and the outflow of particles becomes less intense. Yet the stored magnetic energy remains enormous, continuing to influence the star's emission. The crust endures continuous strain as the internal field drifts slowly through the solid lattice. In some regions, magnetic diffusion rearranges field lines, creating new stresses that build for decades before releasing in sudden flares. This balance between slow creeping motion and explosive rearrangement defines the Magnetar's long-term stability. Its quiet intervals are deceptive. Beneath the hardened surface, energy is constantly moving, reshaping the magnetic skeleton that holds the star together. Cooling and spin down proceed hand in hand. As the Magnetar radiates away energy, its internal temperature falls below 1 million degrees. The superconducting core locks the magnetic field more firmly in place, and heat transport becomes confined to narrow channels along field lines. Surface temperature varies across the star, hotter near the magnetic poles, cooler at the equator, producing uneven emission. X-rays emerge in pulses that match the rotation period, creating the flickering light curves observed from young Magnetars. Over tens of thousands of years, the amplitude of these pulses decreases as the difference in temperature evens out. The magnetic field gradually decays, though never fully disappears. Its decay releases additional heat, prolonging the Magnetar's visibility long after other neutron stars of similar age have faded into darkness. The environment surrounding the Magnetar changes as well. The nebula inflated by the Magnetar wind expands and cools, its luminosity fading with distance. The once bright filaments become faint threads of ionized gas drifting through interstellar space. The Magnetar remains at the center, surrounded by a vast, transparent cavity of its own making. Its radiation now interacts directly with the interstellar medium, ionizing nearby clouds and producing weak radio emissions detectable across light years. In these later stages, the Magnetar's presence is known not through explosive flares, but through persistent rhythmic pulses, steady reminders of the rotation that still continues. The crust, now solid and cool, bears the marks of immense past stress. Deep cracks remain frozen in place, silent remnants of earlier starquakes. Underneath, the neutron superfluid rotates in quantized vortices, microscopic whirlpools that carry angular momentum. As the crust slows due to magnetic braking, these vortices adjust by moving outward, transferring rotation from the fluid interior to the solid surface. The movement is not perfectly smooth. When large numbers of vortices shift suddenly, the entire star experiences a brief acceleration in spin. Such events may recur sporadically over millennia, demonstrating that even a body as dense and rigid as a magnetar remains dynamic. Stability for a magnetar is a matter of balance between three forces: gravity, magnetic pressure, and internal rigidity. Gravity seeks to compress the star further, magnetism distorts it outward, and the solid crust holds both in equilibrium. The strength of the field creates a measurable deformation, making the magnetar slightly elongated along its magnetic axis. These distortions can in theory produce gravitational waves, ripples in space-time radiated as the magnetar spins. The waves are faint but persistent, carrying away a fraction of rotational energy. Over cosmic time, this slow emission may contribute to the magnetar's continued spin down. As the centuries stretch into tens of thousands of years, the magnetar's radiation weakens, but it never ceases completely. Its internal magnetic field continues to decay, releasing heat that leaks slowly to the surface. Flares become less frequent, their intensity reduced, yet the crust remains active. Occasionally, a sudden rearrangement deep within reignites the magnetar, producing a flash detectable across galaxies. Such an event might occur without warning, a brief burst marking the end of long silence. Afterward, the magnetar returns to its steady rhythm, spinning through the cold and empty dark. From a distance, the object appears faint, a soft X-ray source pulsing at intervals of a few seconds. Around it, the remnants of the nebula have dispersed into the galactic background, leaving only faint traces of emission. The magnetar's gravity pulls in sparse interstellar particles, but the inflow is negligible. It exists in near-perfect isolation, no longer explosive, yet never truly still. Inside, the superconducting core and solid crust maintain their slow, unseen dialogue with stresses accumulating and subsiding in cycles that span centuries. This phase of cooling and stabilization represents the magnetar's maturity. It has transitioned from chaos to endurance, from the heat of collapse to the slow persistence of equilibrium. Though its brightness fades, its magnetism remains a silent force, altering the paths of nearby particles and influencing the surrounding space for millions of years. Eventually, as rotation continues to slow and the field weakens, it will become indistinguishable from an ordinary neutron star. Yet even then, traces of its extraordinary past will remain, magnetic scars etched into the crust isotopes, frozen in the remnants of flares, and a subtle imprint on the interstellar medium that once absorbed its light. In its quiet endurance, the Magnetar embodies the final stability of a process that began in catastrophe. The explosive birth is over, but the legacy of that violence continues, preserved within a body smaller than a city, yet capable of holding the memory of a dying star. Even as the Magnetar settles into long-term equilibrium, it remains a restless object. Its crust, frozen into place by immense pressure, continues to strain under the unrelenting pull of the magnetic field within. Over decades and centuries, the internal field drifts, shifting slowly through the dense material of the star's crust and core. The tension builds, invisibly accumulating in twisted regions, where the magnetic pressure exceeds the strength of the solid lattice. When that threshold is crossed, the crust gives way in sudden fractures that release bursts of energy more powerful than any event on Earth. These magnetic and seismic disturbances, known as magnetar quakes, are the source of the most intense flares in the universe short of black hole mergers. The process begins deep inside, where magnetic flux tubes, bundles of field lines, trapped in the superconducting core shift position. Their movement exerts stress on the crust above. Once the crust cracks, energy stored in the magnetic field is liberated in the form of high-energy photons and plasma, streaming outward in milliseconds. The magnetar's surface flashes with temperatures exceeding 100 million degrees, and a wave of gamma radiation sweeps into space. Each flare follows a similar pattern, a sharp, brilliant pulse of energy, followed by a slower decay as the crust and magnetosphere readjust. The first phase lasts only fractions of a second, during which the magnetosphere is flooded with radiation and charged particles. The outburst's power can exceed 10 quadrillion times the luminosity of the Sun. The subsequent tail phase, lasting minutes, comes from trapped plasma oscillating within the magnetosphere, gradually radiating its energy away. From Earth or any distant point in the galaxy, such flares would appear as short, intense gamma-ray bursts, arriving without warning and fading just as quickly. A few of these events have been observed, and their signatures match what theory predicts the unmistakable fingerprint of a magnetar quake. The physics behind these flares is rooted in the interaction between the magnetar's field and its solid crust. As the internal magnetic field evolves, it induces shear stresses that the crust cannot permanently withstand. When the crust fractures, the sudden motion of magnetic field lines through the plasma generates electric currents that accelerate particles to relativistic speeds. These particles emit synchrotron radiation, producing the brilliant flashes observed across the spectrum. The magnetosphere, momentarily distorted by the flare, expands outward and then snaps back, sending shock waves through the surrounding space. In particularly large events, magnetic reconnection occurs far above the surface, ejecting clouds of plasma that carry part of the magnetar's energy into the nebula beyond. After each flare, the magnetar enters a period of recovery. The crust cools, the magnetosphere settles, and radiation output returns to its baseline level. Yet the event leaves behind subtle changes. The rotation rate may shift slightly, and the field geometry can become more twisted. Each quake alters the internal configuration of the magnetic field, influencing where and how the next will occur. In this way, the magnetar's long-term evolution proceeds through a series of violent corrections rather than gradual decay. The times between major flares can range from years to centuries, depending on how rapidly stress accumulates. Smaller bursts occur more frequently, releasing minor adjustments in the magnetic equilibrium. The energy released during these flares interacts strongly with the environment surrounding the magnetar. Gamma rays ionize nearby gas, heating the nebula and briefly increasing its brightness. Shock waves propagate through the surrounding plasma, compressing and re-energizing the filaments formed during earlier stages of expansion. The magnetar's flare thus becomes a recurring driver of activity within its own remnant, reigniting structures that had begun to fade. On longer timescales, this cyclic pattern of outburst and relaxation contributes to the persistence of magnetar wind nebulae. Each flare injects fresh energy into the system, keeping it luminous and dynamic, even as the central engine gradually weakens. Inside the star, the sequence of stress build-up and release continues unendingly. The superconducting core, where magnetic flux is frozen into quantized tubes, shifts as these tubes drift outward over centuries. This slow motion changes the overall field geometry, transferring energy from the core to the crust. The movement is governed by diffusion temperature and quantum pinning forces, a complex interplay that ensures the magnetar's evolution remains active for millions of years. Even as surface activity fades, the hidden rearrangement of the internal field continues. The magnetar's apparent calm conceals deep, steady motion within a reminder that its stability is never absolute. Not all flares are equal in scale or consequence. Minor crustal adjustments may release moderate bursts that slightly perturb the magnetosphere. Major fractures, however, can reshape the field entirely. In rare cases, the energy liberated in a single flare can alter the star's moment of inertia, causing measurable changes in its rotation period. The most powerful outbursts may even produce detectable ripples in space-time, faint gravitational waves radiating outward from the magnetar's distorted shape. These waves carry away a fraction of the released energy, leaving behind a slightly more symmetric configuration. In this way, each flare both relieves tension and helps the star inch closer to equilibrium. Over tens of thousands of years, as the internal field decays, the frequency and power of these flares decrease. The crust becomes thicker and less elastic, reducing its ability to fracture. The star's cooling suppresses some of the motion that drives magnetic diffusion. But the possibility of renewed activity never vanishes completely. Even in ancient magnetars, residual magnetic drift can generate sporadic bursts. These faint echoes of earlier violence serve as reminders of the immense energy still confined within. The field will take millions of years to fully dissipate, ensuring that the magnetar's presence endures long after its light has dimmed. From a cosmic perspective, Magnetar quakes, and flares are among the most energetic recurring phenomena in existence. Their radiation travels across interstellar space, briefly illuminating vast regions before fading into the background. Each event broadcasts the signature of extreme physics, the meeting point of quantum mechanics, relativity, and stellar evolution. To observers in distant epochs, a magnetar's flare will seem instantaneous, yet its origin lies in processes that unfold over millennia. The slow shifting of magnetic fields, the gradual cooling of dense matter, and the eternal struggle between stability and collapse. In the silence between eruptions, the magnetar continues to turn its magnetism unbroken, its energy waiting. It is a monument to stored power, a reminder that even after death, a star can still speak through bursts of light that pierce the darkness of time. As millennia unfold, the aftermath of the explosion drifts towards stillness. The once brilliant supernova remnant grows vast and faint, expanding into the interstellar medium and losing its original shape. What was once a turbulent sphere of plasma now stretches across dozens of light years, its edges thin and translucent, its core filled with fading filaments of gas and dust. The energy that once defined it has dispersed, leaving only a ghostly glow detectable in long exposures of radio and X-ray light. Within this dim expanse, the magnetar remains rotating steadily, its magnetic field still immense though slowly decaying. It continues to power faint emission from the surrounding space, a quiet engine sustaining the last traces of its own creation. The nebula's internal pressure decreases as the energy input from the magnetar declines. The magnetic field that once inflated the nebula relaxes, allowing the outer regions to merge gradually with the ambient interstellar medium. Shock waves have long since faded, replaced by slow diffusion and gentle mixing. The temperature drops as radiation escapes, and what was once an environment of billions of degrees now cools to a few thousand. The gas within the remnant becomes a tenuous mixture of ions and neutral atoms no longer hot enough to glow visibly. Over tens of thousands of years, dust condenses from the cooling material, forming microscopic grains of carbon silicates and iron compounds. These grains drift outward, scattering light from distant stars. Eventually they will join the galactic dust lanes, the same kind of material from which new stars and planets will one day form. At the centre, the Magnetar persists as a small but powerful presence. Its rotation has slowed further. A full turn now takes several seconds. Magnetic braking continues to extract energy from its spin, but the losses have become minimal. Most of its radiation now emerges as low-energy X-rays and faint radio waves. Occasionally a minor flare disturbs the calm, a last flicker of the field's internal tension, releasing a brief pulse before fading again. The Magnetar's magnetic field has weakened to a fraction of its initial strength, but even now it exceeds that of ordinary neutron stars by several orders of magnitude. The decay of this field produces residual heat, preventing the surface from cooling completely. Thus the Magnetar remains warm long after its surroundings have fallen silent. The space around the Magnetar becomes increasingly sparse. The expanding debris thins into the background of the galaxy, blending with the diffuse hydrogen clouds that fill interstellar space. The boundaries of the original remnant blur and disappear. Only the innermost region retains a faint structure, a cloud of relativistic particles still confined by remnants of the Magnetar's field. As the nebula fades, this inner bubble contracts its pressure, finally giving way to the surrounding medium. The Magnetar becomes an isolated star separated from its birthplace by thousands of years of expansion. It drifts through the galaxy, carrying with it the heavy elements it once cast into space. From afar, the Magnetar would appear as a point of invisible energy, detectable only in X-rays or radio pulses. To instruments designed to listen for the faintest signals, it would stand out as a periodic flicker, a pulse repeating every few seconds. The intensity of these pulses depends on the alignment between the star's magnetic and rotational axes. When the beam passes Earth or any distant observer, a brief increase in brightness is seen before darkness returns. Over time, these pulses slow as rotation continues to decay. The Magnetar's life becomes one of repetition and gradual fading, its once violent activity replaced by quiet persistence. Despite this calm, the Magnetar's influence endures. The heavy elements expelled during its birth remain scattered across the interstellar medium. Iron, nickel, calcium, and silicon drift through space, mixing with clouds of hydrogen and helium left over from the galaxy's formation. When these clouds collapse under gravity, they carry within them the fingerprints of long-dead stars. Future solar systems will form from this enriched material, and planets will bear the atoms created in explosions like this one. The Magnetar in this way contributes to the chemistry of future worlds. Its existence becomes part of a much larger cycle, the continual recycling of matter that sustains the evolution of galaxies. Within the star itself, the passage of time continues to erode its internal energy. The magnetic field decays exponentially, converting its stored energy into heat and low-frequency radiation. As the crust cools, superconducting regions in the core shrink, and magnetic flux lines drift slowly outward. Each movement releases a small amount of energy, adding to the gentle warmth that prevents complete freezing. On the surface, radiation emerges uniformly, the once hot polar regions now only slightly brighter than the equator. The Magnetar's temperature falls to a few 100,000 degrees, still hotter than any ordinary environment, but far below the incandescent heat of its youth. The Magnetar's gravitational field remains unchanged, an invisible grip warping the space around it. Its density has not lessened. The entire mass of a sun remains confined within a sphere no wider than a city. Time near its surface still flows more slowly than in distant space, though the difference is imperceptible now. The curvature of space-time that surrounds it endures a silent reminder of the compression that created it. Yet despite its immense gravity, the Magnetar no longer draws in matter. Its isolation in a near-empty region of space leaves it untouched, drifting among faint clouds and cosmic dust. It has become one of the loneliest objects in the galaxy, a remnant of unimaginable violence now reduced to a single pulse, repeating endlessly into the void. On a much longer timescale, even this pulse will fade. The magnetic field will decay below the threshold required to power emission, and the Magnetar will transition into a quiet neutron star. Its radiation will cease, its surface will cool, and it will merge indistinguishably with the background of the galaxy. Only the atoms it once produced scattered across space will continue its legacy. In distant future epochs, some of those atoms may form part of new stars or condense into rocky planets orbiting other suns. A few might one day be incorporated into living matter, linking the death of a massive star to the emergence of life. The dimming remnant thus represents both an ending and a beginning. What was once a furnace of energy becomes a seed of new creation. Its light may have faded, but its influence will persist across cosmic time, encoded in the material fabric of the galaxy. Every atom heavier than helium owes its existence to events like this, to the death throes of stars, whose gravity and magnetism transformed chaos into order. The Magnetar's story, though now almost silent, continues in the quiet unfolding of those processes. In the great scale of the universe, nothing is truly lost. Energy changes form, matter drifts, and every ending becomes the foundation for something new. As the last photons escape from the Magnetar's cooling surface and vanish into the galactic night, they carry the final whisper of the explosion that gave them birth, a faint, enduring memory of light born from death. Long after the light of the explosion has faded, the space once occupied by the dying star becomes indistinguishable from the rest of the galaxy. The Magnetar remains, as its only survivor, a compact sphere of density and silence rotating slowly in a vast darkness. Around it, the debris of the supernova has dispersed, enriching the interstellar medium with metals and minerals that did not exist before its birth. Those atoms, iron, nickel, gold, and carbon, will someday become part of other stars, planets, and living things. The Magnetar's death in this sense contributes to the birth of future worlds. Its life, violent and brief compared to the age of the galaxy, leaves behind an influence that endures for billions of years. Every cycle of matter in the Milky Way carries traces of such events, reminders that each generation of stars inherits the remains of those that came before. The galaxy itself is a vast ecosystem of stellar death and renewal. In its spiral arms, where gas and dust collect, new stars are continuously born from the ashes of old ones. The heavy elements forged in supernovae and magnetar births mix with hydrogen clouds, cooling them and allowing gravity to form dense cores. From these cores, new suns ignite, repeating the process that began the Magnetar's own life millions of years earlier. The remnants of long-dead stars act as silent architects of future systems, providing the raw material for rocky planets, atmospheres, and the chemistry of life. The Magnetar's contribution, though invisible, is therefore fundamental, a small but necessary step in the endless recycling of cosmic material. At the galactic scale, the energies released by such explosions help shape the Milky Way's structure. Waves of shock energy ripple outward through the disk, compressing gas clouds and altering their motion. Over time, these disturbances influence star formation on scales of thousands of light years. The collective effects of countless supernovae drive the circulation of matter within the galaxy, maintaining the balance between collapse and dispersal. The Magnetar's explosion was one of many, but each event adds its own resonance to the galaxy's rhythm. In this way, even a single star contributes to the larger choreography of cosmic evolution, where destruction and creation are inseparable. The Magnetar itself continues to evolve in slow, imperceptible ways. Its magnetic field weakens, its spin slows further, and its heat dissipates. Over millions of years, the field that once powered brilliant flares and nebulae fades to levels indistinguishable from those of ordinary neutron stars. What remains is a dark, cold remnant invisible except to the most sensitive instruments, yet its presence still curves space around it, exerting gravitational influence on the thin dust and gas of its surroundings. Occasionally the Magnetar may wander close to a molecular cloud, disturbing its motion slightly, or pass near another star, altering orbits in a subtle gravitational exchange. These small interactions remind the universe of its existence even when its light is gone. Beyond the immediate vicinity, the debris once expelled by the explosion continues its journey. Over tens of millions of years, the elements it carries will mix thoroughly with interstellar gas. Grains of dust formed in the cooling remnant will drift into dense regions where new stars are forming. Some will become trapped in protoplanetary disks incorporated into rocky planets, orbiting young suns. The iron in those worlds, the gold in their crusts, and the oxygen in their atmospheres all trace their origins to the brief incandescent life of massive stars and their explosive ends. The Magnetar, the small, played a part in that chain of transformations. Its existence marks one link in the cosmic lineage that connects stellar death to planetary birth. Over longer timescales, even the Magnetar's interior will change. The superfluid core will continue to cool until it approaches absolute zero, and the crust will become brittle and inert. Magnetic energy will decay completely, leaving only residual fields frozen within the matter. The surface, once glowing with X-rays, will become dark, reflecting no light. Time will stretch onward, but the Magnetar will persist, an unchanging monument to the forces that once created it. Such objects can survive almost indefinitely, outliving the stars, planets, and galaxies around them. In the distant future, when most starlight has faded and the universe has entered its long decline, Magnetars and other neutron stars will remain as some of the last witnesses to cosmic history. The region of space the Magnetar once illuminated will by then be transformed. The shock waves from its explosion will have dissipated into faint ripples of gas. The nebula will have vanished, leaving only faint traces of enriched material dispersed through the galactic arm. Yet those traces will not vanish from the cycle. The atoms born in that furnace will have found new homes in the hearts of stars yet unborn, in the surfaces of planets, perhaps even in the chemistry of distant living cells. In that sense, the Magnetar's story never truly ends. It simply changes form, passing from light to matter, from heat to motion, from destruction to creation. If viewed from a distance now, the site of its birth would be indistinct, one small region among countless others in the spiral arm of the Milky Way. The Magnetar itself would appear only as a dim point in the radio spectrum, its rotation so slow that its pulses arrive minutes apart. To most of the universe it would seem silent, yet deep within that silence lies the record of an immense event. The collapse of a star, the compression of matter to nuclear density, the amplification of magnetic fields beyond measure, and the transformation of energy into the elements that build worlds. The Magnetar embodies the universe's ability to create permanence from impermanence, to extract enduring structures from fleeting catastrophes. In cosmic perspective, the birth of a Magnetar is one of countless such transformations, yet each is essential. The universe depends on these extremes moments when balance fails and new order emerges from chaos. In the ruins of a massive star, gravity and magnetism rewrite the laws of matter, generating the elements, radiation and motion that sustain the cycle of galaxies. The Magnetar's life and death are part of that ongoing rhythm. Its explosion reshaped its surroundings, its cooling and decay returned energy to the cosmos, and in the endless interplay between creation and collapse, it stands as a reminder that even the most violent deaths can be acts of renewal. Now only the faint pulse of radiation remains spreading outward into the galaxy. Each wavefront carries a story that began millions of years earlier, when a star burned too brightly and reached the limits of its strength. The energy of that moment continues to travel, crossing the spiral arms, touching dust clouds and mingling with the light of countless other stars. In time it will fade beyond detection, its photons scattered among the cosmic background. But in their passage they leave a trace, a whisper of the forces that shape the galaxy, and of the invisible Magnetar that still turns in the dark. Its light may be gone, but the memory of its birth is written into the stars themselves, ensuring that the story of one star's death remains forever woven into the fabric of the universe.